Last chapter, one bucket took us most of the way. But it never quite fit. Look closely, our one bucket model misses at the start. And it drifts away in the long tail. One bucket keeps one clock, a real cell keeps many. So let us add a second bucket. Another resistor, another capacitor, with its own time constant. In Simulink, we simply add one more RC pair to the chain. Now we have two clocks, a fast one and a slow one. And watch the error fall, from about 13 millivolts, down to about 1. Much better, but something is nagging. We are just stacking curves until the numbers agree. When do we stop? 2 buckets, 5, 100. Let us ask a deeper question. Not how to fit the curve, but why it bends this way at all. Until now, the cell has been a black box. Let us open it. Inside are 2 electrodes, soaked in electrolyte. And each electrode is packed with tiny grains of active material. This is where the sodium is actually stored. Let us shrink down into a single grain. At rest, the grain is evenly full of sodium. Now we draw a current. The surface hands over its sodium first. But deep inside, the core is still full. So a difference builds up. The edge runs low, the middle stays rich. And sodium has to move from the crowded core toward the empty edge. This slow migration is called diffusion. And in a solid, it is sluggish. Sodium creeps through hard carbon at about 10 to the minus 15 meters squared per second. The grain is only a few millionths of a meter across. Yet even that tiny trip takes minutes. That is the drift we cannot fit. The surface stays starved, so the voltage keeps sagging for minutes. Now the circuit finally means something. The fast bucket is the surface, the interface reacting in a heartbeat. The slow bucket is diffusion, deep inside the grain over minutes. Each bucket is no longer just a curve. It is a real, physical clock. But here is the subtle part. Diffusion is not one clock. The very surface relaxes first. Then the layer beneath it, then the next layer deeper still. Every shell of the grain has its own small delay. So diffusion is really a whole chain of tiny buckets. A little resistance to the next shell, a little capacitance to fill it. Over and over, inward, engineers call this chain a transmission line. And if you take that chain to its limit, infinite tiny buckets, the whole thing collapses into a single element. The Warburg element, named for Emil Warburg back in 1899. It is diffusion itself, written as one clean symbol. You can even see its signature on an impedance plot. Diffusion shows up as a straight 45-degree line. And this is exactly how diffusion is measured in the lab. You pull a short pulse of current, then stop and let the cell rest. During the rest, the difference inside the grain slowly evens out. And the voltage drifts back. That slow recovery is diffusion made visible. The method has a name, GITT. The galvanostatic intermittent titration technique. From Weppner and Huggins in 1977. So here is our full model. A source, a resistor, and 2 buckets. 5 dials in total. Tuning them by hand would take forever. So we let the computer do it, with parameter estimation. We hand Simulink the real curve and say, match this. Watch the dials move on their own. They start far off. The error is about 20 millivolts. Now the optimizer searches. Each pass, it nudges every value. The resistance settles near 30 milliohms. The fast clock finds 1.5 seconds. That is the interface. The slow clock finds about 90 seconds. That is the diffusion. And the error collapses from 20 millivolts down to barely 1. Notice what just happened. We never told it about interfaces or diffusion. It found those two physical clocks, on its own, just from the data. But a warning, every bucket you add is one more dial to turn. And more dials will always fit the curve better. That is not the same as being more true. Diffusion has endless timescales, so no finite set of buckets is ever exact. The honest goal is the simplest model that answers your question, where every element still means something real. We have pushed circuits a very long way. They now imitate diffusion itself. But they only imitate it. To truly capture what happens inside that grain, we have to stop drawing circuits and solve the physics directly. That is the final step, Chapter 5.